Hello, good evening. My name is Amal. I'm a PhD student from the Cultural Institute of Technology in Germany. Today I'm going to present you something related to our attempts towards modeling of the dimensional error especially in down-facing surfaces and our methods using artificial neural networks. So the agenda of the presentation is like this. So first we speak a little bit about challenges that we face in general for precision in additive manufacturing, some of the pathways that we follow in the PAM² project. Then we focus more on down-facing surfaces. So it's the down-facing surfaces are a major source of our research because of being such a problematic feature. Some of the defects, why they're caused, how they're caused, and then we go into what we are doing with it. And then we will finish off with the results and conclusions and our future work. So the major challenges in precision additive manufacturing, as you are probably aware, are due to first being the nature of the process being multi-physics, multi-scale process. It makes it exponentially harder to simulate and to model. The number of material choices are limited. The material properties, also there's an isotropy in the direction because of the layer-by-layer manufacturing of style, additive manufacturing, as well as a lot of process instabilities, cost due to power distribution, part orientation, build direction, etc. The method with which we are working is to tackle different parts of the problem together. Firstly, we're trying to make all the parts of the machine to be more predictable and controllable. We want to understand all the costs and the effects of different process parameters that work in LPBF processes. We want to enable more advanced process monitoring, controlling, and also develop models for physics-based process simulation, as well as topology optimization. So in addition to some of the presentations you've already seen today, we have also people working on these topics. Our focus lies primarily in the second part, which is to understand the cause and effect of different process parameters. We want to contribute towards improving the amount of process knowledge we have and to hopefully improve predictability in the process to achieve first time through production of components with good dimensional accuracy and surface quality. So down-facing surfaces, why they are a big issue for us is because they have the worst surface finish of any surface in additive manufacturing processes, especially when you start going below 45-degree angles. The surface finish starts to deteriorate quite rapidly. Our aim is to investigate the effect of process parameters for down-facing surfaces so that we're able to print lower angled surfaces with lesser surface defects and better accuracy. Why? Because we want to pretty much remove the need for the building of support structures, which necessitates further process steps. In one way, we hope to contribute towards improving the productivity of the process this way. So, yeah, I think Umberto touched upon this a little bit. The main cause for defects in down-facing surfaces is the formation of dross. Dross is formed primarily because of the overheating of powder, which is due to the low thermal conductivity of powder compared to the bulk of the part. Heat is not effectively transferred to the build platform, which results in formation of this overheated zone, and therefore dross is formed. So our approach to tackle or to attempt at optimization is by developing new process parameters, strategies for down-facing surfaces in particular. So all of our process parameters are varied only within the red area over there. And so this is our capable level of our process parameters that we're testing. So that the DOE over here shows us our matrix of our experimental trials, the dimensions of our, this is our 45-degree overhanging feature, and yeah, the build direction. So first, we started off by doing a regression modeling. So we wanted to statistically analyze once we had built them and measured them. So yeah, we use an image processing technique. We wrote code on MATLAB to batch process our images. Basically, it's quite simply just we grayscale the images, apply a threshold for all of them. We then do an edge detection, and then we scan the whole image to detect the edges, draw our edges, and then measure the deviation between them. We measure the thickness of the samples because our postulation is that our process parameters, when everything else remains constant, our process parameters are affecting thickness. So we use that as our classifier. We did some statistical modeling using MATLAB. So we did the regression modeling to identify the effects of the main effects as well as interaction effects of the different process parameters on our dimensional error percentage. So using this, we were able to understand how our measured error percentage was varying when we looked at the different levels of our power, of our scan speed, as well as scan spacing. Then we also did some ANOVA analysis to basically understand the most significant process parameters for us in terms of effect on the dimensional accuracy. So once we had this regression model, we were also then able to use that for prediction. And our maximum error in prediction, at least using this method, was 5% away, but we have not validated this model yet. This was only on the test of our own training data. So we thought, why not also try artificial neural network modeling, since it is known to be quite a accurate way of modeling processes. Artificial neural networks are in general inspired by biological neural networks. They also have nodes and synapses, and each neuron is somewhat related to a biological neuron. The main application or example where artificial neural networks are used is in problems where you want to take decisions or make estimations. This is a general structure of an artificial neural network. We have a lot of input neurons where you feed the input layer, which in our case is our process parameters, and we have an output layer. The output layer is the dimensional accuracy. So the main idea is to understand what is the relationship between the output layer and the input layer based on the process parameter, based on the input data. So our proposed solution for our artificial neural, we tried a number of different artificial neural network models. This is the one that we stuck with because it's the one that we achieved our lowest mean square error possible. So in this case, we have an input layer with 5 different process parameters. We have one hidden layer with 3 neurons, and one output layer with one dimensional error being our percentage. We had to reduce our data set because we had a total of 144 data points, but we realized that we were overfitting our data a lot, so we had to reduce them to 90 because we had a lot of repeated process trials. So in order to prevent this overfitting, we reduced the number of our data points. Okay. So the result of our artificial neural network was that I forgot to mention. So what happens is we have when we give our input the data, we also have to assign different we call these hyperparameters, which are weights and biases and learning rate, which are then transmitted to the hidden layer. And at first we assign them randomly. After we feed forward this, we then have to, based on the prediction, the artificial network automatically sets new values for our weight and bias and learning rates, depending on the error that's achieved. So each time we feed forward and have a back propagation, we call that as an epoch. And after we noticed that we were achieving the best mean least mean squared error after 5 epochs. So which was at a 0.2855 millimeters. So we split our training data into 3 different sets. We had a training set, which was 70% of all of our data points. We had a validation set, which was 15%. So the training data set is used to build the model at first. We then use the validation set to tune the hyperparameters and everything, after which we have our model readily created. We then have our remaining 15% points to actually run an unbiased test of our model. And this was at epoch 5 when we had the least error of 0.2855 millimeters. But this 0.2855 millimeters in our case, it still represented an error of 10%, which compared to our linear regression statistical modeling is not as good as that. But we postulate that because it's because of the limited nature of our data. At first, when we started building the design of experiment, we were not planning on using an artificial neural network to model the process. But since then, it has gotten better. So to come to the conclusions now, we focus mostly on to develop a process model for unpacing surfaces of laser powder bed fusion processes. We use first linear regression and to understand the main and interaction effects. With that model, we have a maximum error of 5%, which is again only to our training data. So it should be really good. The NN model has a worse error prediction rate, but we hope that once we have actually included more data points, it would get better. So this study is still ongoing. For future work, we're also investigating, this is the graph of our volumetric energy density along with all the measured dimensional error percentage. So for points 15 to 24 with the same volumetric energy density, we notice a lot of fluctuation in dimensional error. So we want to investigate why that's caused, and it's probably because of position and orientation. So that's one thing we're looking at the moment, and also we're conducting our validation right now to actually be able to conclude if our models, both the models that we develop, are any good or not. So that was it. Thank you.
Thank you, Amal. Questions? So, can you comment on the generalization of this approach? I mean, you give some input to your neural network based on your machine, so you perform some actual measurements, right?
Yeah.
Then you can have as an output, once you put other parameters, possible expected geometrical error. Can this approach be generalized also to the process in general, to other machines, or maybe with a lot of data coming from different machines? In your opinion?
So I don't know. The thing is, what we're doing at the moment is in general only going to work for the machine that we're working on, which is the ProX 320. But that is another thing that we want to investigate. So because there are other machines also in 3D systems like the 500 and whatever. So we want to investigate that once we have when we have a validated model, we want to then investigate if that model also holds true for other maybe even electron beam. I don't know, but maybe. So yeah, that's something that we will do in the future.
Thank you. Other questions? Well, if not, I will close this session. I think it was a very interesting presentation. So thank you to Amal. And I think